has been recorded. Okay, welcome everybody. And so today we are going to talk about hypothesis testing. We will continue on hypothesis testing, but this time we are going to do hypothesis testing for two samples or two population samples. Now, last time we did a hypothesis test. Let us say that we hypothesize that the average price of houses in Brooklyn is $300,000. So we're going to test the hypothesis that the mean is 300,000. But we are looking here at all the houses in Brooklyn put into one population. But suppose we hypothesize that the average price of houses in Bed-Stuy is the same as the average price of houses in Borough Park or in Wicksville or Clinton Hills. We can take any two populations. We say the average age of male and female students in McGivers College is about the same. That's a hypothesis. Or we can even hypothesize that the average age of males is greater than higher than the average age of female. That is, the average male student is older than the average female student. So now we have two populations, and we're going to test the hypothesis that our proposition is true. We are going to test the hypothesis that our characterization of male and female students is the same. The average GPA of transfer students is not different from the average GPA of students who came in as freshmen. That's a hypothesis, okay? So I'm going to illustrate this by pulling up some PowerPoint slides so that we can look at some examples. Now, I'm going to go through the normal test hypothesis, doing the calculations of the average of each subpopulation, calculating the standard deviation, and then selecting a Z statistic or even a T statistic if the samples are small. And then we'll go through the calculations. Now, when you're using SPSS, what SPSS is going to do is to give you confidence intervals for the two populations. And if they overlap, then you are not able to reject the null hypothesis. If the confidence interval do not overlap, you will reject the null hypothesis. But let's look at a simple example. If I cannot find the SPSS printout, I will post one for you in the what do you call it, in the website, or next week when we get back together, I will find a suitable what do you call it, a suitable example. Or let me see, for now, let me stop this recording and hello, I'm sorry, I cut off the mic. Okay, as I said earlier, I'm going to pull up a PowerPoint slide. Welcome, Sharifa. So we're going to use the PowerPoint examples to test the hypothesis for two populations. As I was saying before, we were joined by other good friends. we are going to practice hypothesis testing for two populations. But I'm going to go back and sort of refresh our minds, refresh us on hypothesis testing generally, beginning from one population to two populations. Like I said, suppose you were to propose a hypothesis that the average price of houses in Brooklyn is $300,000. So you test a hypothesis where mu is equal to 300, or you can say the average is equal to 300,000, okay? And the alternative hypothesis, the alternate hypothesis will be that the average price of houses is not equal to 300,000. Or you can propose a one-sided hypothesis, which says that the average price of houses is more than 300,000. Or the alternate could be that the average price of houses is less than 300,000. But you are testing the population, one population, that is all of Brooklyn together, okay? You are testing all of Brooklyn together as one population. But what if you hypothesize that the average price of houses in Bed-Stuy is not different from the average price of houses in Borough Park? You are now splitting Brooklyn into two populations. And so you want to compare two subpopulations of Brooklyn. Or you can test the hypothesis that the average age of male students is the average male student is older than the average female student, or the average student, the average GPA of a transfer student is not different from the average GPA of a student that comes in as a fresh person. Okay, these are all characterizations of populations, but you split the population into two. The average wage of union workers is not different from the average wage of non-union workers. That's a hypothesis. Or you can say the alternate, that the average age of union workers is higher than the average age or the average wage of non-union workers. You have split the population of workers into two, and you're comparing them. And that is what hypothesis testing for two populations is. All right, so let's pull up the slide. All right, are you able to see my slide? Hello?
Yes, Professor. Yes, Professor.
All right, okay. See, I want to know if we're on the same page. Okay, that's why I ask those questions. All right, so let's proceed. So like I said, I'm going to refresh on hypothesis testing. And the last time we did one sample hypothesis test. And one sample hypothesis test is where you like take the entire population and you simply propose that the average is equal to so and so. The average is 300. The average is 20, okay? But you can take that population and split it in two and compare one subpopulation to another subpopulation. So let's begin from one population hypothesis test. Okay. Now here, like we said, in order to test a hypothesis, you must define the hypothesis. You have to define the hypothesis. The average age of houses in Brooklyn is 70 years. The average age of houses in Brooklyn, 70 years. The average price of houses is 400,000. You have to define that hypothesis, okay? So, and we're going to explain the process of hypothesis testing as we did the last time, and there is a 6-step procedure, okay? It's a 6-step procedure for hypothesis test, okay? For example, this is where you define the problem. Remember, when you define the problem, you define the hypothesis, you say exactly what you are looking for, okay? We're saying that the machine is expected to produce 595 units per day, okay? And so 505 595 units per hour, per minute, okay? You can hypothesize that consumers prefer Coke over all other cola drinks, okay? And so the 6 steps, and I'm going to make this bigger, and you see it bigger now, all right? Okay, so you state the null and alternate hypothesis. You must state a null hypothesis and then state an alternate, okay? You state the level of significance. I'm going to test at 1% level of significance. I'm going to test at 2% level of significance. I'm going to test at 1.5% level of significance. You can even test at 25% level of significance, even though a 25% test, which is the 25% possibility that you're going to be wrong, okay? Which is really a very generous and very lax kind of hypothesis. But if you test the hypothesis at 1%, you're taking a chance that there's a 1% chance you could be wrong, okay? Which is more conservative, which I would think is more reliable, okay? Then you identify the test statistic. We are using the normal distribution, and so our test statistics is either a Z distribution, if your sample is large enough, more than 30, or a T distribution if your sample is small, less than 30. Okay. And then you formulate a decision rule. And the decision rule is very simple. You have what you call the critical Z value, and then the calculated Z value. So your decision rule would be if the calculated Z value is greater than or equal to the critical Z value, then you reject your null hypothesis. You say, well, the null hypothesis does not hold. If your null hypothesis is that the average price of houses in Brooklyn is 400,000, and your calculated Z statistic is greater than or equal to your critical Z statistic, then you reject the null hypothesis that the average price of houses is 400,000. And you accept the alternate that the average price of houses is not 400,000. Or if it's a one-sided hypothesis, then you conclude that the average price of houses is greater than 400,000 or less than. It's a one-sided hypothesis. Your alternate could be less, it could be more, or it could just be, it is not it. All right? All right. So, I mean, I often give an example using somebody who was arrested for stealing somebody's money. And so the question was, how much money was in this, how much money was it that this man stole from you? And the person said, $20. What kind of money was it? I mean, was it a $20 bill or two $10 bills? Or was it a mixture of $5 and $1 bills or $10 bills? And the person said it was a $20 bill. Okay, so they searched the accused and found out single $1 bills more than $20. And so they said they rejected the hypothesis by simply saying the bill in this man's pocket was not $20. And so that resolved the matter. Okay? All right. So we state the null hypothesis, the alternate hypothesis. All right? Okay. So I'm going to give an example here. Okay. Just give me a minute. Let me fix something here. All right, I'm going to do an example here. Okay, a machine is designed to produce 595 units per day. And so what you do in testing a hypothesis is to take a sample of daily productions. So you take a sample today, you take a sample for 35, 40, 50, 60 different days. And each day you record, you take a note of how many units were produced. So today was 600, the other day it was 500, the other day was 400, another day it was 300, another day it was 650, and so forth and so on. And then you calculate the average. Okay? And in this case, we showed an average of 625. That was the average we got. But does this mean that the machine produces more than 595 per day? Not necessarily. In statistical analysis, that is not how we do it. Because the variances could be so wide that you're going to get any number. And so you have to take into consideration the standard deviation. The standard deviation is 400. Then maybe the average production is not up to 595 a day. Okay? All right, so let's move on. All right. And so what we do is we collect a sample, a data sample. We looked at 38 days. The sample mean we calculated was 625. The sample standard deviation was 65. We select a level of significance, for example, 1%. It could be 2%, it could be 3%. Okay? Now, the way, again, I believe everybody here knows how to find out the test statistic. So this is the critical value, the critical Z table, and the critical Z value. So this is critical. Okay? So you determine the critical value by looking it up based on the level of significance. Okay, if your level of significance was, say, for example, suppose you take a level of significance, and I'm going to give an example, 0.005 or 0.5%. Your Z star would be 2.58 or 2.57. Okay, so you determine your critical value, and then you calculate the Z value, which is the calculated Z value, which will be X bar, this 625, minus your null hypothesis, which is 595. So let's see if we solve through this example. Okay, so you state your null hypothesis. Your null hypothesis is that the average should be 595. And this is a one-sided hypothesis. Okay, this is a one-sided hypothesis, and so your alternate hypothesis, HA, or sometimes people use H1. It could be H1, it could be HA. Okay, I said that mu is greater than 595, and the reason we say that mu, the alternate, is more than 595 is that we have a sample mean that is already higher than 595. And so we state the alternate to be greater than 595. But we want to know if statistically that makes sense. The whole idea is not that because you see 625, you conclude that you're rejecting the null hypothesis. No, it depends on the standard deviation. Okay, it depends on the standard deviation and also on the sample size that you're using. Okay, uses a sample size that is small, you're more likely not to reject the null hypothesis. All right. If you use a large sample size, you are more likely to reject the null hypothesis. So we already know that our critical Z is 2.33. We calculate that. And then we get our calculated Z. So I'm going to call this calculated Z. Okay, so this is your calculated Z. And so your decision rule will be if the calculated Z is greater than the critical Z, then you reject the null hypothesis. Reject. Reject means you are rejecting that the average production is 595. So this is a one-sided hypothesis. Therefore, you conclude that the machine produces more than an average of 595 per day. Because once you reject one, that means you're accepting the other one. You are reaching the conclusion is now the alternate. That's what you're doing. And since we reject the null hypothesis that the average is 595, we are now concluding that the average is more than 595. Now, this is one population. We are looking at this particular machine, okay? All right. And so this is the same problem that we looked at. You can see we tested it at 0.005, okay? And again, once more, we reject the null hypothesis because we have 2.8 as the calculated z, okay? Still looking at the same problem, okay? And of course, here, this is what SPSS will do for you. As you can see, and let us emphasize this. If you have an SPSS printout and you have a confidence interval, from an SPSS printout, and that confidence interval goes from negative to positive, then what is the conclusion? The conclusion is that you are not able to reject the null hypothesis. If the confidence interval of the hypothesis test goes from negative to positive, then you are not able to reject the null hypothesis. If the confidence interval is either all negative or all positive, then you reject the null hypothesis. Everybody understand that? Okay.
Can you repeat it?
Okay.
Can you repeat it?
Okay. Sometimes I will do the hypothesis testing for you. I'll go through the calculations, but I'll use an SPSS software. And if you get a printout like this, there are two ways you can make your decision for a hypothesis test. Either you use the Z, and if this calculated Z that you see here is less than the critical Z, then you are not able to reject the null hypothesis. We provided an example. If the calculated Z is greater than the critical Z, then you reject the null hypothesis. Otherwise, you are not able to reject the null hypothesis, okay? The alternative way is if you look at a confidence interval printout, and the confidence interval, you can see there's a lower and there is an upper. Going from the lower to the upper, if the values go from negative to positive, then you cannot reject the null hypothesis. Is that clear?
Yeah. I got a question, Professor. Would there ever be a case where the calculated Z value is greater than the critical value? But
of course, we demonstrated it the first time.
No. I'm saying, would there ever be a case where it's greater, but the confidence interval is negative and positive? Would they ever?
Never.
Okay,
no.
Okay, all right.
That never happens. Okay, because they give you the same result in different ways. They lead you to the same conclusion, but in different ways. Okay.
Okay, got it.
Okay. So if the confidence interval is either all negative or all positive, then you must reject the null hypothesis. You get that? Okay.
Yeah.
So I take it that you get it. All right. As you can see here, the calculated Z is 0.831, and the critical Z is 2.576, and therefore, in this case, we cannot reject the null hypothesis. All right? And you can see the result shows from negative to positive. Okay? And it never happens that if Z is less than Z star, you get a positive or negative. No. Once you have a negative or a positive, the calculated Z will be greater than the critical Z. All right. This is the same problem. This is the same process. Okay. So you can see here the calculated Z, sometimes it's called a T if the sample size is small, is 3.8. You can see you have a positive. Once the calculated Z or T is greater than the critical Z or T, you would have a positive or a negative. It doesn't happen any other way. Okay. This is an illustration of your homework problem, which we did the last time we were here. All right. All right. So now we are looking at hypothesis testing for two populations. Okay. Two sample test of hypothesis comparing two populations. And here's an example. Is there a difference in the mean value of residential real estate sold by male agents and female agents in South Florida? Again, that is where you are looking, comparing two groups, male agents and female agents. Okay? Is there a difference in the mean number of defects produced on the morning shifts and night shifts at Kimball Products? So the average number of defects. So the morning shift and the night shift, is there any difference in the the average number of defects? Okay. Maybe the guys in the night shift are feeling sleepy. So this is why they produce less. All right. And the guys in the morning shift, they come fresh. So this is why they produce more. Or maybe the sleepiness has no effect. Or maybe the night shift people do not feel sleepy. Okay. Is there a main difference between the number of days absent between young workers and older workers in the fast food industry? The young workers, feel like they want to prove themselves, and so they work very hard. Or maybe they are more irresponsible, and so they really sometimes don't come to work because they don't have to pay all those bills. All right. Okay. So let's go to our hypothesis test. Okay. For the two different populations. Okay, this is two sample hypothesis testing of house by family size. And here's a summary. Okay. And so you take a sample of houses. You take 44 houses of two-family houses and 49 houses of one-family houses. Okay, and ask yourself, what is the average size of the houses in terms of square footage? All right, and so you calculate the sample mean. So this is the sample mean. Okay. This is the sample mean. For each for the two types of houses. And you get a sample standard deviation. Okay. This is the size of the houses in square foot. This is the average age of houses. So we are looking at two different kinds of averages here. The average size of the house and average age of the houses. All right. And so like we said, when you're doing a hypothesis test, you must first of all define the problem. And so we have defined the problem. Is there a difference in the average age of one-family houses compared to two-family houses? That is our hypothesis test. Okay? And so, I mean, that is our problem. That is our problem. Is there a difference in the average age of one-family houses compared to two-family houses? Now, once we do that, we have to state that proposition mathematically in statistical language. And so the null hypothesis, which is, this is your null hypothesis, okay? Let me label that clearly. This is your null hypothesis. Okay, your null hypothesis, and this is your alternate hypothesis. So the null hypothesis will be that mu1 minus mu2 is equal to 0. If the average age of houses is the same between two populations, what happens when you subtract those averages? If average 1 is equal to average 2, then average 1 minus average 2 will be equal to what? 0. Am I correct? Hey guys, are we still there?
Yes.
Yeah.
Okay. So is it clear to you that if the average of 1 is equal to the average of 2, when you subtract average 1 minus average 2, what are you going to get?
0.
0. So this is why we state the null hypothesis that mu1 minus mu2 is equal to 0, which in English says there is no significant difference in the average age of one-family houses compared to two-family houses. The alternate hypothesis, okay, I'm going to take this out. The alternate hypothesis is that the difference between the average ages of houses in the two types of houses is not equal to 0. This is a two-sided hypothesis because they're simply saying that they are not the same. They are not equal. That's all you're saying. You are not saying that one is higher than the other. You're not saying that one is lower than the other. So what you have here is a two-sided hypothesis. Okay? And in effect, you're saying in English that there is a significant difference in the average age of one-family houses compared to two-family houses. Your level of significance is 0.005, which is half of 1%, and your critical Z will be 2.576. And so the methodology will be to calculate the Z. Now remember, we're going to compare calculated Z against critical Z. So we take, excuse me, mu1. I don't know why somebody put a comma there. Just give me a minute. I'm going to stop share for a minute, see what I'm doing here. Okay. All right. So let's continue. Okay. So we're going to take mu1 minus x bar 1 minus x bar 2. So we subtract the two sample means. All right. We subtract the two sample means and we divide by the formula that you see here, S1 squared over N1 plus S2 squared over N2. And we take the absolute value, okay? Forget about the sign. Use the absolute value. And so 49 minus 62 over 29 squared plus over divided by 44 plus 20 squared divided by 49 and we take the square root of that calculation. Trying to see if I can get rid of this. No, it's not going to let me do that. But know that there's nothing there. Okay. And so the calculated Z will be 12.91 divided by the arithmetic that you see there. And the calculated Z will be 2.29. And so the decision rule is that if Z, the calculated Z, is greater than Z star, we reject the null hypothesis. And our results show here what? That the calculated Z is what? Tell me. I'm waiting for your answer. Is the calculated Z greater than the critical Z? Can I hear the answer to that?
No.
Okay. See, the calculated Z is less than the critical Z. Therefore, we are not able to reject the null hypothesis. And what is the null hypothesis?
That it'll be greater or equal to 0.
That they the same?
We are saying that we are not able to reject the null hypothesis that the averages are the same. You get
There's
that?
Yeah, there's no significant.
Yeah.
There's no significant shift. Change.
There's no significant difference. We're not talking about
difference,
change.
sorry.
Okay.
Difference, right.
Okay. There is no difference in the average houses, the average age of houses between the two kinds of houses. Okay. So we are not able to reject the null hypothesis, and that is simply that. Okay. I already showed you what the SPSS will do. It will give you a confidence interval. It will give you a calculated Z, and you can use either of them. Okay. If I ask specifically that you must use the calculated Z, then you have to demonstrate to me that you know how to compare the critical and the calculated. Okay. Now, if I ask you to just give me an answer, you can use the confidence interval. You either get a positive or a negative, or you will get a crossover from negative to positive. And once you do get a positive to negative or negative to positive, then you cannot reject the null hypothesis. That is simply how to do it. Okay? There is nothing magical about it. That's just the same problem illustrated. So we're not going to go through that. Same thing here. And so you can look through those problems. This is another problem with houses in Brooklyn older than houses in Staten Island. So the same illustration. So does anybody have any questions?
Dr. Egby, I do have a question.
Sure.
This PowerPoint slides that you're using, which ones are they? Because I'm trying to follow along. I came on late, so I didn't want to interrupt you, but I'm trying to follow along. And the ones that I printed, the two sample tests for hypothesis, I don't see some of these in it.
Yes, because I'm using a different one, and I'm going to post this one.
Oh, you haven't posted it yet. Okay, so that's why I wasn't following. Okay, my bad.
All right. Ain't nothing bad. I mean, at least it shows that you went into this website and you downloaded something. Okay.
Okay.
That's an old lecture. And so I'm going to post this one because as I go from semester to semester, I try to improve on what was done the previous time. So I'm going to post this one. I might even add some other slides to illustrate the SPSS. And so when I come in next week, I'm going to go through that enhanced slide first. All right?
Okay, thank you.
All right. Just to show you, to illustrate to you what I said today about the two sample hypothesis test using SPSS. When we had access to our lab and when we did this in the classroom, actually we learned how to use SPSS, which I love to give to my students, because when you go out there, that's what you're going to see. You're going to see all the software. And
so we don't have access to that now anymore?
We have the lab, but we're not in the classroom. And if I ask you to download the lab, I mean, the SPSS is going to cost you money. But in the lab, it was free. And
right,
so
but we don't have access to the lab anymore?
Yeah,
the computer labs?
Yeah, you have access to them. You have access.
So if we use the SPSS, that will give us the answers for most of the homework that you give us?
If I ask you to use raw data, yes, it will. If you use SPSS data, yes, of course. If you put your data into SPSS, you get a result. You know, one thing I could do is next time I will illustrate how to do the SPSS. And so if you want to go to the lab and practice it, that's good. Because students in the past, you know, when I used to teach both statistics 1 and 2, students in the past have come back to say, honestly speaking, when they go to grad school, it was easy. Because that's what's going to happen. And in grad school, they're not going to ask you what you know and what you don't know.
Right. The reason I'm asking that is because if it's available in the computer lab, then we can run the test there and then make sure that our answers are correct in the other, you know, format. So that's why I'm asking.
Absolutely, absolutely. Some students in this class, like last semester, went to the lab and used SPSS.
Okay,
because
so
they probably learned it in Start 1, especially when I was teaching it myself.
okay, so I just want to confirm we have access to SPS in the computer labs.
Yes, it's free.
Okay, good to know. Thank you.
All right. Any other questions? Okay, all right. Thank you all for stopping by. So I hope you do your homework assignments. If you have problems, please, in the name of God, get back in touch with me.
Professor.
Yes.
Before you go, can you just briefly go over ANOVA and the F test?
That's next week.
All right, no problem.
Yeah, that's next week or the week after that.
Okay.
We are going to do ANOVA. It's part of this class. We're going to do ANOVA.
All right.
Okay. Any other questions? All right. Thank you for coming. And I look forward to seeing you next week.
Professor.
Yes.
When can we have like a one-on-one with you?
Send me an email. Tell me what time you want to be available, and I will set up a Zoom.
Okay. Thank you.
All right.
Thank you, Professor. Have a good one.
Okay. Everybody have a good night.
Same. Good night.
All right.